Our next speaker is Prof Duncan Haldane, who will talk about entanglement and topology in quantum mechanics. The Q&A session will be moderated by Prof Liu Wenxiang from the Nanyang Technological University. Prof Haldane, please.
The clicker. Thank you. Just one comment on Hugo's talk. He didn't mention to you that the three-dimensional Ising model describes what happens in your kettle when you boil it. The boiling of water, and this critical point is the 3D Ising model. Okay, I'm going to tell you about some stuff to do with quantum mechanics, and I'll see how far I get with all of this. But basically, as we understand quantum mechanics better, what's emerging is, lots of strange possibilities, and the hope that new materials and technology will emerge from new studies of quantum mechanics. So the modern laws of quantum mechanics are established starting about 100 years ago by these gentlemen, and so far, all tests of quantum mechanics have shown it's correct. But just because we know the laws of quantum mechanics doesn't mean that we know all the amazing things that quantum mechanics allows to happen. And that's really what's been happening now. And starting around 1980, we already heard that Richard Feynman started discussing what would happen as we tried to build computers down to the atomic level and invented the idea of quantum information theory. And this has gradually merged with insights from condensed matter and atomic physics now. And people now are talking about we've entered the second phase of the quantum revolution, the second quantum revolution, where we're focusing on all these new possibilities by considering quantum information theory. So what is quantum mechanics? Of course, Niels Bohr's atom in 1913, his model was like a little solar system, the electron going around the nucleus, except its angular momentum was quantized in units of Planck's constant. Around about 1926, the more modern version emerged, and I will say it's discussing putting electrons in boxes. Bohr called the orbit of the electron an orbit, and that language has stuck as now we call the box which electrons go into as an orbital. And Heisenberg's uncertainty principle says if the electron is in the box surrounding the atom, it's somewhere in there, and it's a fuzzy cloud centered on the nucleus and not the orbit of Bohr. So we can think of a hydrogen atom and a hydrogen ion as the box being empty in the first case, and the atom, the box is filled. And now, we can actually see the images, maybe not of the ground state of the hydrogen atom, but this is an excited hydrogen atom called a Rydberg atom, where the electron is in a much larger box, which is out at a larger radius, but there we are. So, Pauli exclusion principle says that two electrons, which is something called fermions, cannot be in the same state. So what defines that state? In addition to the position, basically, or the place where you find the electron, it has an internal degree of freedom, its spin, which is like a little spinning top. And we can put two electrons in the same box, little orbital, if we put them in with their spins in exactly opposite directions. And quantum mechanics says that the two electrons have to, something called a wave function has to be odd under interchange of the electrons. So we have to put the spins in up, down, or down, up, with a minus sign relating the two things. And it doesn't matter if it's up, down, and down, up, or sideways to the left and sideways to the right. And that's a maximally entangled state of two electrons. And then in high school chemistry, we have this picture of boxes that we put electrons in, and you see you put them in two. You pair them up in this entangled pair, or you put them in singly, and you build up the periodic table. Okay. So the chemical bond that binds us all together, that binds atoms into interesting clusters, and we're such a cluster, is a maximally entangled state. The two atoms are held together really by the electrons that go into the space between the two electrons, and you can put two electrons in a chemical bond, one up and one down, and they have to be in this antisymmetric singlet pair. And in fact, this is probably the only quantum mechanics that most chemists need to know. You know, you've got a picture, and then you can think of these as little building blocks. But there's just this entangled state is everywhere. But the central theme in the new approaches to quantum physics seems to be this property of entanglement. And it only becomes really unusual or strange when it happens over distances large compared to atomic distances. Entanglement is everywhere on the atomic scale in chemical bonds. And as Einstein pointed out the curiosity of what the curious property of entanglement in quantum mechanics. But now, from being a philosophical question, it's evolved into being viewed as the fuel which will drive future quantum information processors. So despite Einstein getting a Nobel Prize, not for relativity, but for the photoelectric effect, one of the second quantum effects to be discovered, Einstein fell out of love with quantum mechanics and was denouncing it around 1935. And he pointed out the entanglement property, which he felt was so crazy, it had to be wrong. And he was sure that it would prove quantum mechanics wrong. And there was some other theory to replace quantum mechanics, which quantum mechanics approximated. So he called it spooky action at a distance, but Heisenberg came up with a much more polite name, entanglement, or the German versions of that. And around about 1935, Einstein's collaborator, Podolsky, went to the New York Times and told them about Einstein have proving quantum mechanics wrong. And it made the headlines. Einstein was very angry because he thought that the physicists shouldn't wash their dirty linen in public, and he stopped speaking to Podolsky, although he continued to collaborate with Rosen after that. But the problem was, if you make this bond or this pair at a large distance, and one electron is pointing up and the other's electron spin is pointing down, and you measure this one, and you find it's pointing up, you'll always find the other one is pointing down. And that vaguely sounds like you violated the relativity principle that some information might have traveled faster than the speed of light. In fact, that's not true in this case. But anyway, Einstein found this a totally disconcerting idea, and he proposed this EPR paradox. And various people went on to think about the paradox and refine it. And in fact, the Nobel Prize a year ago went to the people who, starting in the 70s and then culminating in the early 80s, actually went and analyzed John Bell's clarification of Einstein's objections and showed that quantum mechanics passes the test 100%. Okay. And so we know quantum mechanics was wrong, and this was right, and Einstein was wrong in his challenge to it. But what he pointed out turns out to be probably the most important aspect of quantum mechanics, which is a true aspect of it. Now, the entanglement is very stable on the level of the chemical bond, but over large distances, it's very fragile against getting the decoherence, which means the particles stop being entangled with each other and get entangled with the environment instead, and any information is lost. But Aspect's experiments use photons rather than spins, and now we have this entanglement. Started off under Lake Geneva, but now we've got the Chinese Weipan have got entanglement between the Earth and satellites in orbit, and we've produced entanglement with photons over large distances. Okay, where's quantum information in this thing? Classical information is stored in a bit, which is basically a switch which is either up or down or on or off. So you can think of the little magnetic domain like the Ising model, where the spins are all pointing upwards. Magnetized upwards would be 1, and magnetized downwards would be 0. And you can maybe flick the two by driving some current through the system to make all the spins reverse. Quantum information is stored in a single spin. And someone mentioned the Heisenberg model. The spin can point in any direction. The only thing is you can only measure its component along one direction of your choice. But the quantum spin, or the qubit, can be viewed as a direction pointing in any direction you want. So it's clearly got a larger information content than just up or down. It's got a direction. And any system with just two quantum states is equivalent to such a spin, so it doesn't actually have to be the spin of the electron. So classical information is unaffected by reading it or copying it. In fact, it's kind of difficult to get to classical information because when you get rid of your cell phone, you have to go to a whole procedure to get rid of all your personal details which are embedded in the chips on your phone. Quantum information is much richer, but it's also much more fragile. And a fundamental principle there is that you cannot copy a qubit. But you can actually do very strange things like teleportation with the information. So one of the basic properties is this no cloning property that I cannot, if my information is encoded in this qubit here, I can't get another qubit and make an identical copy of it, which I could easily do if I was pirating some rock music or something like that. The best you can do is actually transfer the information from one qubit to another qubit, but you have to erase the first qubit in order to transfer its information to the second one. That's the no cloning theorem. And so let's see. And in fact, the procedure which comes sort of out of Star Trek for this is the teleportation. I start with what's now called a Bell pair, an entangled pair of qubits or spins. I stretch it, maintaining the entanglement. And now I've got two qubits in this region here. I've got a local target qubit that I want to copy, and the unknown state of the half of this Bell pair. There are two qubits here, there are 4 states, so I do a measurement, and there are 4 possible outcomes to that measurement. I pick up the telephone and call someone at the other end of this entanglement pair and tell them what the measurement said. They can then, depending on what the measurement revealed, they can do a procedure on the last qubit which will make it an identical copy to the original one, and now the information is lost down here. So we can have strange things happening with qubits. Okay. So this has led to the idea that entanglement is the fuel for quantum information processing. But it's, as I say, it's entanglement over large distances as a fuel, not short distances as in the chemical bonds. And how do we produce it? Well, two systems become weakly entangled if they're placed in contact, but we want to we get a Bell pair, this complete up-down minus down-up entanglement. And there's a protocol for doing that. You can bring things together, make them interact a little bit with a gate. I switch on a gate, I switch it off at exactly the right time, and I'll start off with 2 things which are up, and I'll end up with this up-down. But this is very delicate. It requires you to the gate has to be just right. You have to switch off at the right time. So I'm going to say that topology has actually led to a different way, on paper at least, of achieving some of this stuff. So around about 1980, condensed matter physicists who study solid and liquid matter, regular matter, not particles and things, they found there were two strange effects which were found. At that point, people vaguely thought they understood, in principle, they understood everything, which is, of course, a bad point to be, because nature will suddenly show you that you don't understand nothing. And the 2 things were, the main one was what Klaus von Klitzing described, the quantum Hall effect, and I found something in magnetism. And these things had apparently no obvious relation to each other, but they turn out to be examples of what we now call topological quantum matter. So topological matter differs from ordinary matter because it's basically described by whole numbers, like the whole numbers that Klaus described in his talk. And whole numbers can't change continuously. So if I have some region where the whole number is -2 and the other is 0, there actually has to be a boundary where the number changes. It's not a smooth boundary. So we actually find that at the edges of topological matter, we generally find something interesting going on. And that was what people had missed up till this point. So basically, the topological properties of materials cannot change continuously. And that makes them kind of robust against dirt and disorder and things, because in the usual materials, in the silicon wafers, you have to be in a clean room, you have to be extremely careful that little bits of hair and stuff come from the workers, doesn't damage the silicon chip. The space suits there are to protect the chip, not the workers mainly. And anyway, so that's the thing. But so what is topology? The classic example in mathematics is, again, the classification of closed surfaces by what's called the genus, which means the number of holes. And the number of holes in a surface is either 1 or 0 or whatever. It can't, a sphere with 0 holes, you can easily change its shape a little bit. You can change a football into a rugby ball, but to change it into a donut, as we'll see in a minute, you have to, which is, I suppose, this picture, you have to do some violence to it. So Gauss, the great mathematician, he discovered lots of things, but the thing he found was the most amazing, he thought was his own discovery, which was the most amazing thing, was if I take a sphere with a surface area of 4 pi r squared, you learn in high school, it's got a curvature called Gaussian curvature, which is uniform, which is called 1 over r squared. I multiply the two together, I get 4 pi. What he found was if I deform the sphere, change its shape into soccer balls or whatever, or mugs, that number stays 4 pi. If it's a bagel or a coffee cup with 1 hole, the number is 0. 2 holes minus 4 pi minus 8 pi. So he found that when the integral of the curvature is much more complicated, it still adds up to a simple number, which just counts the number of the holes in the system. Okay. And later, around 1944, the Chinese-American mathematician Chen generalized this Gauss-Bonnet formula for physical surfaces into a much more abstract formula involving algebraic surfaces, and his generalization turns out to apply to the quantum problem. In mathematics, there's no Nobel Prize. Apparently, Nobel was prejudiced against mathematicians for personal reasons to do with his wife, but there's a Fields Medal, which Hugo had, but if you're older than that, older than 40, you don't get it, so they created a few Nobel-like medals, and one of which is the Chern medal with the Gauss-Bonnet-Chern formula on it. Okay. So in heavier atoms, electrons in a group of orbitals can become locked together, so they're always parallel, which gives rise to magnetism. And you can see you've got adding up these spins. If the spin is s, the elementary spin is called spin 1/2, so 2s electrons add up to a spin, but an important thing is whether there's an even or an odd number of electrons. And that was something that was missed until the work I had in around 1981. And people there thought of magnetism in this language. You just lined up a load of magnetic atoms in a certain pattern, and nothing particularly had happened. But it turns out that you can get a state of a one-dimensional magnet again, the ground state, where you actually split. This is a spin 1 atom with 2 spins here. You can split the spin 1 into 2 spin halves, one on either side, and combine them to form this entangled bond here. And you see you get left with something at the edge, half of a spin. And that's typical of topological stuff. You've got something funny happening at the boundary. Well, at the time, this was kind of very controversial in the magnetic community and etc. I won't go into that. I had difficulty publishing it. But science is a question of experiment. And the material sciences came up with, they came up with a spin 1 chain with nickel atoms in some organic background. And eventually experiments were done, and it was found that the predictions were correct. And a lot of things came out of that controversy. So controversy is actually very good in science. It gets people interested in being on one side or the other side of the question and doing experiments. Okay. And really, there's the meme of this. I'll come back to that if I have time. It's a line of people. People have generally have 2 hands if they don't have an accident. And if you line them up in a row and they hold hands, you'll find one end of the row has a single hand that's free to wave around, and the other end of the row of people has a single hand that's free too, which is what's happening in this spin chain. And they put it on my Nobel diploma, this picture. Okay. So the other thing that happened was the quantum Hall effect. And Klaus von Kissing described it, and it's now, of course, the thing that's replaced the kilogram in Paris. And the crucial thing there is there's a whole number involved. The conductance of this thing, which is 1 over the resistance, is a whole number n times universal constants E squared over h, which is 1 over 25,310 ohms. Okay? And this wasn't, the topological nature of this also took some time to discover, but basically in the quantum Hall effect, as Klaus found it, electrons are going around on a little 2D surface. They're going around in little periodic circular orbits because of the magnetic field, but when they hit the ones at the boundary don't complete their orbit. They hit the thing, and instead they kind of skip around in skipping orbits in the opposite direction. So you find there's this edge state, which is, again, a characteristic of topology, and it means that Klaus's experiment worked, basically. It explains why he got a robust answer for this thing. So the integer Hall effect, as it was called, no sooner had people sort of come up with a kind of explanation of it that said the quantization should always be an integer, the fractional case came along, when instead of being an integer 1, it was a 1/3. Well, actually, when reinterpreted, this is still an integer, but what got replaced in the formula was, instead of the electron charge E, it was 1/3 of the electron charge. And that's because this new state involves charges which are 1/3 of the electron charge, a typical thing in topological systems called fractionalization. The elementary charge turned out to be E by 3, so this is still an integer number times E by 3 squared over H. Okay. And there's the device. You can see the device wouldn't get you a job at Intel in their fab, the soldering, but this shows the robustness of topological stuff. It doesn't matter that this is a rather cruddy-looking piece of soldering, right? That showed the effect. Okay, and one of the weird things in this is you've got the most interesting thing, I would say, there's this edge state that goes around the edge. The fractional case now, if you remove an electron from it, it leaves a hole behind, but that hole splits up into 3 charge 1/3 holes. So it fractionalizes. And these 1/3 holes have an interesting property. If you exchange them, you would expect to get fermions which exchange get a -1 when you exchange them in the quantum factor, quantum wave function, or bosons that get a +1. No, they get a phase factor e to the I pi by 3. And so this is called braiding. So you move these things around each other, and they give you funny numbers, which you didn't expect. And that's recently been proved by experimentally. Funny thing, you have a device which contains some of these fractional E by 3 charges, and there's some kind of interference pattern that I won't go into, but each time an extra 1/3 charge jumps into the little central pigeon of this device, it causes a kind of earthquake shearing of the diffraction pattern, and you have to have 1, 2, 3 things enter the device before you get back to where you started from, showing this 1/3 business. Okay. So the Laughlin state and the early fractional quantum Hall states are what we now call, quote, abelian, a nice mathematical word for abelian states. But then the generalization to something called non-abelian states was pioneered, and this is the states which can hold quantum information in it. So when you have the little defects or vortices in that thing, instead of just a phase change of the wave function when you move it around, you actually change the wave function in a more fundamental way, and basically you have a qubits in it. And in principle, you could do quantum computation on paper, and the interest in this thing was stimulated by Alexei Kiev, who pointed out that these things could, in principle, give you universal quantum computation. And the basic thing there is that the little excitations, which now, these were actually in a 1/2 filled case, and they carry a 1/4 charge in this example. You can only add these little blob things. 2 of them can be added at the same point. You cannot add them individually at different points. You have to add them both together at the same point and then pull them apart. So you had added a charge 1/2, but you pulled it apart into this 2 charge 1/4 objects. And when you pull them apart, the history of how they were pulled apart is reflected in an entanglement pattern inside this material. And for every pair of vortices you add 1 extra qubit to this system. You had to start with 2, and then so 4 is the minimum. And if this qubit is represented as pointing upwards, there'll be another one that looks like this, where you can't tell, if you can't see the entanglement pattern, it looks identical to this, but it actually reflects the qubit pointing that way. So the quantum information is stored in the entanglement pattern. And if you start moving these things around and braiding them around each other, you stir up the entanglement pattern that contains the quantum information, and you change it, and you're doing a computation. And this is the idea. Now, since you can't see the entanglement pattern until you bring these objects close to each other, they're protected from the environment. So if I took a gun and shot a hole in this thing, the chances of me destroying the quantum information is exponentially small. So because the information has been spread out. The only danger is when you feed the information in, the two things have to be close to each other. And then when you read the information out, you have to bring them close. But this means you can do many, many cycles, on paper at least, of the computation. Only the input and output are the danger points where you risk to lose things. Okay. So this is a kind of inspiring idea. Okay. And actually, Microsoft put a lot of money into this, and in fact, they found that you could get these interesting objects not just in quantum Hall systems, but in superconducting type systems, and they're called Majorana zero modes. So far, we haven't got a qubit. People thought they would get a qubit very quickly. It hasn't happened yet. I've heard there's some progress at Microsoft, but now they've kind of taken everything inside the company and stopped collaborating with universities. So they kind of got serious about, international, as we heard, the competition between nations on quantum computing. Let's see where. So Majorana zero mode, this fellow Majorana discovered that you could somehow write the electron as a complex number and factorize it into its real and imaginary parts, or the orbital. So the amazing thing about Majorana zero modes is I've got this, what I told about a qubit, either empty or filled, 0 or 1, and there's something that prevents you putting a downspin particle in here, so it's actually a topological superconductor. The Majorana zero mode is exactly like the halving of the spin I talked about, except now I've got something even stranger. The electron orbital has been halved into two half orbitals. The box you put the electron in has been split into two halves, which are distinct, physically separated from each other, and when you pull it apart, there's this entanglement trail which couples the two, and which is what I showed in the other graph. And this is actually this amazing thing. If I put the electron in here, it's also in here too, and it's a very surprising thing that you can factorize this. And this is how, the topological computation scheme is done in all this picture here. Basically, when the things are separated, when I pull the box apart into two halves, I can't tell if it was empty or filled before I pulled it apart. The information about empty or filled is hidden, and then it can be recovered by joining these boxes up with other half boxes and recording things. Okay, and there's no delicate timing for the gates and things in this construction. That's why, on paper at least, people think this will help you do both protect and do the information. I see. Now, it's a beautiful dream, of course, and fusion energy is also a beautiful dream, which works well on paper, so I'm not telling you to invest your pension funds in, it's your decision if you invest your pension funds in topological quantum computation companies, but, I think at least on paper it's a possibility, and it seems that more and more things that are realized as theoretical ideas finally end up getting realized as actual real life. Okay, let's skip that. Basically, the superconductor splits the orbitals into two bits, and they can rejoin in another way, leaving this half orbital at the end as a kind of even more rich version of the half spin at the end of the chain. So, there's a lot of progress in quantum stuff, so who knows what will actually happen. So I just want to mention a couple of interesting developments. First of all, regular qubits have been used to simulate some of this stuff and actually show that you can get some of these non-abelian braiding. We'd like to actually have it done in a real device, not in a simulated device, but that's very encouraging. And most recently, it turned out some work I did found that you could have the quantum Hall effect, the integer kind that von Claus described, could actually occur in zero magnetic field with, just as a consequence of ferromagnetism, no big magnetic fields. And it actually occurs at a higher temperature than the original thing. And just this year, over the summer, a number of groups, someone who found one example, and then the people have leapt in, and more examples are being found all the time, that you can make so-called flat band systems, basically with these twisted bilayer moire patterns, and you can see there's a much larger scale pattern than the original graphene pattern when you have these two layers here. And this large scale allows you to get very flat bands. It narrows the energy. And this year it was actually been finally discovered that not just the integer Hall effect in this model here, which was a realization in Tsinghua 10 years ago, can occur, but now these flat bands in these systems at least show the fractional case. And again, at a much higher temperature and with no magnetic field than the original thing. So it's promising that new platforms are emerging which will actually may become practical for seeing some of these exotic quantum states. And I think that's my time. And I'm exactly finished on time. Thank you.
Hi, Professor. Thank you very much, Professor Haldane, for very exciting talks on the entanglements and topology in quantum mechanics. I'm sure the audience want to know more from you. All right. So the floor is now open for questions.
Hello, Professor. I'm Mohani Siddiq from Singapore Academy's fellow. So actually, I studied quantum spin chain in my PhD research. It's a spin to quantum spin to chain. So we try to detect the Haldane gap, actually, but unfortunately, we cannot. So that's kind of
too small.
It's too high.
Oh, okay.
I think. So we did it in the National High Magnetic Field at Florida, USA. So yeah, we still but you said in your presentation there is like more to the story of the theoretical discovery of the gap in the integer spin chain. So can you elaborate more to the story? I mean, it's kind of like many people don't believe that because of the reasoning based on the magnons, right? At that time, so
yeah, it was very controversial at the time because people believed in took their models from spin wave theory in higher dimensions, the classical limit of the Heisenberg model, and actually there was an exactly solvable and integrable model of the kind that Hugo was talking about that was incredibly confusing to the field. There was a one-dimensional exact solution, not just of the Ising model, but also of the one-dimensional Heisenberg model, again, especially with nearest neighbor interactions and spin a half. And it was very complicated. Hans Bethe discovered it while he was a postdoc, I guess. And he went on, of course, to do things like discover how the fusion in the sun works. But he started off on the spin chain. And he guessed the right solution. He guessed by luck the solution.
You mean better answered solution?
Yeah. So he didn't actually know why it worked, and he thought it would work for 3 dimensions. It doesn't. And it took about 60 years to discover the very complicated mathematics that makes it work. So the people in the magnetic community generally couldn't understand the mathematics, but they could see the pictures that came out. And the pictures looked superficially exactly like what you'd get from spin wave theory. So they thought they had a confirmation of spin wave theory for the spin half system. No one had noticed in that community that the specific heat was exactly a factor of 2 too small compared to spin wave theory. And it's, in fact, the excitations of Bethe's model are something called spin a half excitations called spin-ons. But it took a long time to learn all that stuff. So people had their prejudice about spin wave theory working. They thought 1 over the spin was something like Planck's constant, a continuous number that varied between 0 for infinite spin and 2 for spin a half. And they thought everything should behave continuously. But now the topology to do with actually tells you that S is an integer or a half integer number. It's not a continuous number. And this was not part of people thinking at the time, so it was very controversial. But in the end, experiments work. Experiments, both numerical and physical experiments, have proved all this stuff, and it turned out to be, it was great that people fought so much over it because they developed all kinds of new techniques which would be useful for other things after that. Yeah.
Thank you. Yes.
Yeah, good afternoon. Thanks a lot for the talk. I'm Melanie and I study material science and now I work on photocatalysis, so I only have a basic knowledge of quantum theory, but what I remember is that quantum mechanics mostly is related to probability and that the measurement influence the results. So I wonder, why does that not affect quantum computing, or that you would lose the information in the measurement?
Yeah, no, you can't measure what's actually, you have to do a measurement at the end of the experiment, or end of the computation. Although nowadays people are coming up with protocols where you actually you measure some things which don't affect the information in a way to error correct or to do things. So yeah, so you want to avoid measuring the information. Once you've measured what your information is, it's lost. But you can actually do measurement. So the current standard is noisy intermediate scale computing. And there you maybe just you could start with 10 copies of your quantum computer, all doing the same thing. And you're not allowed to investigate what their state is while they're operating. Otherwise, you lose the information. But what you can do is you can compare them. And if you find that one of the 10 is different from the others, you say, oh, that one went wrong, and I throw it away. Then you've got 9 left, right? The problem is at some point you've run out of copies, and then you have no idea what the answer is if the answer is valid or not. But you have these ways of doing partial measurements to determine whether something went wrong. And really, we would like to protect it in some way. And on paper, what this topological stuff supposedly does, but we won't know if it's really a good scheme or not until we actually have a topological qubit, which has been a long time coming. Yeah.
Thank you.
Yes.
Yeah. Hi, I'm Patrick, with the last name that is too hard to pronounce, I think. I'm a postdoc in Recon, and I work on topological qubits, like basically trying to build what you talked about. And I mean, we do like all kind of systems. We do like semiconductor nanowires, TIs, 2D materials, and so on. And when I was a bachelor, I was sitting like in a lot of things with like Kauvenhoven, when this whole Microsoft stuff started, like the big promises, we just have to do like this, this, and this, and we will have one.
Yeah, overconfidence.
Yeah, and I mean, what I actually want to ask is like, what is your personal opinion about the state of the field? Because I have a little bit the feeling, like I'm somebody who has to build these structures, kind of, and I have the feeling right now we are kind of always running for like new things, as I said, like the 2D materials, which are basically more and more a pain in the ass to make. Yeah. And also like further away from like any maybe robust way to make them on a larger scale. Yeah, what is your opinion about that? Like,
yeah, I mean, the actual platform is still up for grabs, right? I mean, I'm hopeful about, but you know, whether the quality of these zero field fractional devices will improve.
Like we have molecules, for
the
example.
molybdenum tantalide or whatever, or penta graphene pentalayers on boron nitride. Yeah, I mean, yeah, the Microsoft people, I've heard from people at Microsoft, they say they've got much better control over the devices. And when they checked out, they decided that Leo's devices were not in the right ballpark or something.
I mean, we had the big retraction. Like
the retraction,
We hurt like the field, so that's why I'm asking. Like,
it was a kind of, So, you know, the jury is out on this thing. On paper, it's great. Yeah, there's a whole issue of fermion poisoning and things like that. Stray fermions coming in for these Majorana zero modes. I mean, the dream is these much more complicated things which haven't really found the realization, except as toy models of Fibonacci anyons, which are supposed to give you universal quantum computing and stuff. So yeah, I mean, it's still vaporware in that sense, certainly. You know, it's a good experience for you. I don't know if you've become disgusted or despondent about it and they're going to move on to other areas.
I'm a physicist, so I still like it from a physical point of view. But I mean, like as I said, like application-wise, I have more and more doubt that we will see that.
Yeah.
My lifetime, maybe. I don't know.
Yeah, well, qubits in general are getting better, and it's kind of interesting that people are able to see some non-abelian type stuff in toric code in simulating it with regular trapped ion qubits, which was quite surprising, and use measurement techniques to probe the state. So what we're really after is looking how to get a exquisite kind of control. I mean, the previous quantum mechanics before the second quantum revolution, I guess, would be something like taking a hammer, smashing something, and looking what the pieces were. Now, instead, it's probably more like trying to play basketball to keep the ball kind of in the air and gradually tap it and manipulate it to do things. So we're trying to get a better control over quantum devices. And I think, something is going to come out of this. I mean,
Let's hope so. I mean,
Yeah.
that's my job. So.
Yeah.
Thank you.
Thank you. Yes.
Yes. Thank you so much for your very interesting lecture. I'm in fundamental biology, so for me, this borderline science fiction.
Yeah.
And because I'm in fundamental biology, so we have a lot of rules and regulation and ethical concern. For example, gene editing in embryos is not allowed, and I think for good reasons. So my question to you is, in quantum computing and mechanics, are there ethical concerns, or do you think there should be ethical concerns? And are there any regulations in place?
Well, it's not obviously dangerous, except the intelligence agencies are worried that if you can decode RSA or whatever, you'll be able to read all the messages that they've been sending for the last 30 years, and maybe they've dropped the name and address of their top spy in the other country. Right? So they'll have to do. So they're pretty concerned if they want to be the first to know if any of this stuff works, because then they're exposed. But ethical things, I mean, right now the main ethical thing is probably to make sure that people honestly report their data, right? Which is a general ethical thing throughout science these days.
Right. Thank you.
Thank you. Any more questions? I have a very general question, which is quite relevant to the gentleman just now asked. The topological states in quantum systems, which is currently quite a popular subject for the students to study. So I would like to hear from you that because it has immense potentials in materials, in engineering, and in computing, as what you just mentioned over here, what would be your advice to the students, the young researchers that want to go into this area?
Well, it's an area where people have been extremely excited about. Now, there are other possibilities. I guess it's at least there are also these interesting edge states which go one way on some of these samples, and I've heard that at least some places are thinking about, can you use any of this stuff for interconnect? So it's not just topological quantum computing as part of it. The whole feature of topological materials and topological band structures is something that the people who did huge ab initio calculations, who said, these other theorists are doing toy models and we're doing the real stuff. The toy model is extremely useful because they can show up. You can do calculations with them, and you can actually see unusual things happening. In all the ab initio work in the past, no one actually thought to look carefully at the surfaces, so they never noticed that there was all this extra interesting stuff going on.
Right.
So there's a huge amount of work just on topological materials, and of course people in their proposals will say, we hope this will do something for quantum computing, but for example, whether or not it's viable, I don't know, but for example, I've heard that one of the big problems is interconnect. 25% of the energy in all these server farms is actually wasted in the interconnects of the quantum devices, and at least some places are kind of looking to see if these edge states could provide a better kind of interconnect, although there's whole issues about contact resistances and things.
Right, the interconnect.
So there are actually possibilities for other kinds of applications, although we'll find out, right? There's certainly a huge concentration of interest And experimentalists love showing the movie of the coffee cup and the donut changing into each other.
Right.
They're just amazed that they're measuring something in the lab and it's got some connection to all this fancy mathematics, right?
Okay. Excellent. Any more questions? One last questions? Yes?
I just wanted a little bit of clarification in case I didn't understand what you were talking about. You have a qubit in a topological system, and the way you described it was that you would split the orbital, and then you would have your electrons entangled between two split orbitals, right?
Well, it'd be one electron.
Sorry, one electron, but you split your orbital.
Yeah.
So then if that's your qubit, how do you do just like a basic qubit operation? Like,
Yeah,
would you excite, you're not exciting the electron.
No,
in this
you actually, the first one is not a qubit. It just tells you whether it's you've got an even or odd number of electrons in it. But for every additional pair you add to the thing, you get one qubit. So the elementary qubit is actually 4 of these objects. And if you started off, if the top pair came out like that and the bottom pair were like so, you could call that the upspin state of the qubit. It turns out if you had actually created the same arrangement but split, the left side was split this way and the right side was split there. For that particular example, that corresponds to a 90-degree on the equator state of the qubit. And if you braid these things around each other, you kind of mess up or link in their entanglement patterns. So it's a fermion number in this case that's being fermion parity plus or minus, which is being manipulated. The two states of the qubit, either suppose the number of electrons is even, then the two states of the fermion numbers would be plus plus or minus minus, right? And that's the two states of the qubit, the up and down. But then a combination of those would be pointing sideways. So the braiding operation mixes this up and allows you to rotate the qubit.
Okay.
The analog of the gates or something like that.
Yeah, so in a more specific sense, you'd still do an excitation between the two split orbitals.
So the original kind of on paper idea is you actually move these things, but now there are other schemes where you do some kind of measurements and measurement-based ways to braid them rather than physically moving these things around. But basically, there's information. Every pair, you can only add these systems to the system as pairs. You can't add a single one at a point. You can only add them as 2 of them at the same place and then pull them apart. So each one you add, you've got one extra qubit degree of freedom in your system. And so you can't, because the things have the Z2, or they kind of, do things twice, you get back to where you started from. It's not a universal. You can't make all possible gates. The next one is something called Fibonacci anyons, which is stuff that exists with toy models, and people are all the time hoping that something called the 12/5 state might be that. But there's no. People are fairly convinced that what they're seeing is this one I showed. The one they really want is the Fibonacci anyons, whether that, and who knows, right? But the fact you can start to make these things in zero field instead of these, huge amounts of Teslas, and instead of millikelvin, it's more like Kelvin, right? Is a huge advance of possibilities. And because we haven't got these new devices down to the same level of cleanliness and thing. But who knows? I mean, it's a total surprise, actually, that suddenly this summer somebody worked out the key thing was to make sure you got a ferromagnetic order spontaneously appear in these Moray systems. And once that happens, it turns out, it seems that you get this stuff. And more than one example have now been found, and people going around, wherever you can get the ferromagnetism to occur, you seem to find this.
Thank you very much.
Thank you very much, Prof Haldane.
Yes,
Prof Liu.
so time's
apologies
up,
to
yeah.
interrupt, but we're just about out of time. Thank you very much again,
Thank you
Prof
very much.
Haldane.
Let's give a big round of applause to Professor Haldane.